Like this was the problem from S to D, right? From one source to one destination. If you can solve this problem, then single source to one destination will also be taken care. So what did we talk about in this implementation? That we will begin with int array that we called level, and the level array will be of size g dot size. So this was our first step, and then we said level of s will be already 0. Right? And after that we go with the DFS approach, and DFS approach said take a boolean array of. Did not
defining the
this is C++. If it was Java, it was int level square bracket is equal to new. In C++ we don't have to do. Now visited also g dot size, and we will initialize visited array with false. We will say memset visited false size of visited. So this is initialized.
Java is
Yes. Arrays dot fill visited false. If you write
when we inside the array or define the array, what will be the size?
by default it will be initialized with false only boolean array. Yeah, but this trick will be used many a times if you are taking a global array and you want to reuse. Or imagine if you want to initialize the entire array with 5 or int max. So this arrays.fill can be used. Now visited is done, and after that we say we take a, for BFS, Pawan, what do we take? A queue, right? So we take a queue of int. This is our queue. And now before starting BFS, our first thing we used to say was queue.push, and we'll push the source vertex, because that is where our BFS is starting, and we say visited of S is true, and then we begin with our while not queue.empty. We go and run our BFS over here. So these are the steps that we discussed. Now in BFS what we do, let's take the first vertex out, queue.front, and we also say queue.pop because we want to remove that vertex as well. Now get all the vertices which are adjacent from this, and those vertices we will say will be at level 1 now, right? So we say, now how do we get all the vertices of this? We say vector of int, yeah, in Java it will be g.get of x, because x is the vertex you took out. So here we will say adjacent of x are g of, here we will say g of x. In Java it will be g.get of x. So once you got all the vertices which are adjacent to x, Pawan, are you able to follow? Any questions? You're not able to follow? No? Okay, so let's see. See, what we are saying is, in graph, when you are at vertex 0, you want to do BFS from that. Or BFS used to say what? That you start with this vertex and put this vertex in a queue. That is what our BFS starting point was. After you have put 0 here, when you take the first vertex out of the queue, what do you put back in the queue? You remember level order traversal of binary tree? Let's do it same way. So if this is the left child, this is the right child. When you have taken 0 out, you have printed 0. Now who should go in the queue? Connected nodes. It's left child and right child. Now imagine if this for n-ary tree, then all the vertices which are reachable from this guy, they all should be put in the queue. That is as simple as that, what we used to do in level order traversal of any n-ary tree. Same way, if 0 is the vertex, now our graph is a map of vector, right? And when we say it is map of vector, we are saying in that map, if 0 is the key, at 0 key, we are storing all the adjacent vertices of 0. 1, 2, 3, 4. Let's say these were the 4 vertices. So the way we are storing is 0 is the key in the map, and at that key we are storing a vector of these 4 elements. So from the map, if I know the key, that key is 0, and if I want to get the value, how do we get the value out of a map? If key is known.
We take one vector,
We'll store
map to that key in that vector.
exactly, yes.
That was the whole vector.
Awesome. So that is what we will do. So exactly, if you see here, that's what I did. So what I said is, from Q we took the first vertex out, and we are calling that first vertex as 0. Like in our example, it was 0. Now for that 0, we want to get its vector. Its vector will be obtained from the map. So G is our map. To G we are saying, if 0 is the vertex, give me entire vector of 0. So this line will give me the vector, and that vector I am putting in adjacent of X. This makes sense? Now when you got the vector of all the vertices which are reachable from X, you are saying, okay, now one by one I will put them also into the Q. That's where the loop will come on this vector. Right? Yeah. Now how do we put this in the Q? All the adjacent vertices of X. How do I write loop over this vector? Yeah, can you speak so that I can type on your pen? ADJX is a vector. I want to, let's say I want to print all the values in the vector for
ADJX dot size.
yeah, int I0. How many values the vector has? ADJ X dot size, yeah, right, and then I plus plus. Now you can see, like, this is like printing an array. We know 0 is the start index, size is giving the size of the array. Now from this vector, the values that are stored in this vector are the vertices, correct? So I get that vertex out. Again, to be clear, I'll say, okay, this V vertex that I'm getting out is ADJX of I. So this will give me the values in that vector, right? Now what I want to do with this V is the question. I got a vertex. Check if it is visited or not. If visited of V is false, only then we want to consider it. In level order traversal also we used to do the same thing. If something that came out, if it is already visited, we never put it back in the queue. Right? If it is not visited, we say q dot push of V. V's level also we want to update. We say level of V is equal to what? Yeah, previous one, from where we reached V. Who was the one in our code written here? Who gave us the path to V?
Of X plus 1.
This X. See, X, we got the adjacent vertices of X, and those adjacent vertices of X, V is one of them. So for V, I can say the parent is X. I can say level of X plus 1. Right? And if I also wanted to remember the path, I would have said parent of V is equal to X. But that we are not doing in this problem. And since you have put V also in the queue, one more thing remaining is V should be marked as visited also. Visited of V is true. Right? Because once you have put something in the queue, it should not be kept again. In queue, we only put those nodes which are not visited. So this is something that we do. Now if you keep going like this, think of it, what will happen? For every vertex, we will keep updating its level from the start vertex, because every time we are adding from the parent. And if we see it with an example, let's say if this was 0, this was 1 and 2, and this is 3, what essentially we are saying is its level was 0, this guy reached 2 vertices, this and this, so their level we updated to 1. From 2, if I end up reaching 3, so this 2 is my X and 3 is the vertex reachable from X. So I'll say, okay, your level is 1 plus the level of 2, so which is 2. Right. So that way, if we keep on going, you will notice that this will update the level for every vertex that is given to us. And now imagine here I don't break the loop. I'll let it complete. In the end, can I say return level of D? Will this work?
Yeah. But it will find for all the.
Yes, because it is connected.
Yeah, because it is connected, it will work. But if it was not connected, then this will be a problem. And then the action I need to take here is I should have initialized this level array with infinite values, right? Because the initialization should happen there. But here in the problem statement, I think we said somewhere given a connected unweighted graph, so we don't care about that extra case. Yeah.
S is equal to D.
Yeah, so ideally this is not optimized version, because if our problem was like this, from 0 you have 1 2 and you have 3, then you have 5, then you have 9. If we are searching for the shortest path from 0 to 2, the current way I have written code, it will run till the end. But ideally 0 to 2 immediately should have broken at this stage and said, hey, 2 has level 1, so that is the distance from 0 to 2. So that would be an optimization we can bring in, and that will come here. We can,
Before diagram.
sorry,
Before one.
before one?
Like you do one diagram.
Yeah.
Can you explain that? In second problem, I have mentioned.
Yeah, so 0, 1, 2, 3, let's say 4, let's say 5 is reachable from here,
Draw a line from 2 to 3.
line from 2 to 3, perfect.
So
Now,
when I start with 0,
yeah, when you start with 0,
I'll go with 1 and
the level of 0 will be 0, right? Yeah. Then you will go with,
so remove that.
this is 1, this is 1.
So 0 to 3 is not there, and there is one more line from 1 to 3. Now I have a scenario.
Yeah, so give me the graph, I'll update. So I'll draw green edges. Yeah, so you have a graph here. Let's see. This graph is saying you have, okay, you have 0, then you have 4, from 4 you have 2, then you have 3, 1, 5, 4 is connecting to 5, 0 is connecting to 3, and that's it, right? So this is your graph.
I want from 0 to 5.
From 0 to 5 you want. Okay, tell me how will our algorithm work here?
So first 0 to 3 is 0 to 4.
So this is 0, 0 to 4 will be 1, 0 to 3 will be 1. Now,
So I'll remove 3.
now you will remove 3, fair. If you remove 3,
I'll add it to 1.
so here it will become
2.
2, that's it. Then you will remove 4. When you remove 4, 4 will update 5 to 2.
But I'm getting 3, sir.
You are getting 3 as an answer for this graph.
Yeah. I mean, expected is 2,
Yeah.
but my output is 3.
Okay. So we can take a look at your code, what exactly you are doing. But here you see, right, when 3 comes out, 3 will just update 1. And then when 4 comes out, 4 will update it to 2. And ideally, if algorithm is correct, this should have been the answer. This is one of the test cases. Okay.
Sir, and one more thing, like
Yeah.
in test cases while inserting the nodes,
Yeah.
one is 1 to 3 and another one is 3 to 1.
Oh, then maybe something wrong with the test case. Has everyone solved this problem? Okay. If people have solved, then there should not be an issue.
No, sir, not this
S
one.
is equal to D and becomes 0 first.
Yeah. Here we were writing. Now, where should I check that case? Before updating level or after updating level?
After updating.
After updating. If S is equal to, sorry, if V is equal to D, then I can say return. Yeah. It's unfortunate, my N key doesn't work, so I have to copy it from somewhere. Okay, let's take this entire thing. Yeah, N return of level of V. So this way it will break. This is what you're saying.
S is equal to
If S is equal to
D.
okay, in the beginning you can say. Oh, so that is one more optimization that Dinesh is suggesting.
Very test case.
Oh, there is a test case like that. Yeah. So if S is equal to D, this is our best case. You can say we don't even need to calculate anything. If S is equal to D,
This code will work, I think.
huh?
This code will work, I think.
Which code? This code will work?
Why did
Because we
initialize
push
now
things,
this?
yeah, that's okay. But
Oh, you're saying if we do not initialize, then also it will work, and where it will work, we can quickly see. Then what will happen is, no, it may not work because when you are popping out S you already marked visited here. When you popping out S, you will never go inside this, right? Because S is already marked visited. So this code may not work if we don't put that case.
But it works.
I don't know. Your implementation might be different, but ideally, if you see this implementation also, so if it is, let's say 0, 1, and 2, and this. So when you have put 0 in the queue, here when you are taking 0 out, 0 is marked as visited already. Its level is 0, and okay. Ideally, Teja, you have written this here. You have written like this.
No, I return.
If it is written like this, it will work. You agree, Dinesh? Yeah.
I return integer.max.
Int.max, and you are returning only inside. It will never go inside this if one vertex is visited.
What I did is just after that, if I check that condition.
After this if.
Yeah.
Then for visited also you are
Equal
checking.
equal to D, and return level of.
Yeah, that certainly will work because after this if condition, if you check, then certainly you are checking for visited vertices also. Then that will work. That makes sense. Yeah, and it's better to put this check outside if. Then you don't have to handle that S is equal to D separately. So it is not the same code. And many times when you say, right, my same code is working, it will. Okay, so let's submit this. Okay, so your one case is not working.
No, sir, not this one. Next one.
Or next one.